So let's start by talking about why a star's mass is so important. Mass is really the key property that controls a star's entire story from birth to death. Now, a star's mass determines its full life cycle. In other words, whether a star is small, medium, or very massive completely changes how long it lives and what happens to it. So, mass affects how the star forms in the first place, how it produces energy during its lifetime, and what kind of object it becomes at the end, like a white dwarf, a neutron star, or even a black hole. So, if we want to understand a star's story, we need to know its mass. And that brings us to the next point, how we actually measure it. And we can't just put a star on a scale, of course, right? Instead, we rely on gravity to tell us how much matter a star contains. So, the best way to do this is by studying binary stars, systems where two stars orbit each other, and their motions give away their masses. Now, to see why binaries are so useful, we need to think about how gravity shapes motion in space. Gravity pulls objects away from moving in a straight line, and without gravity, they would just keep drifting forever. But in a binary system, the two stars don't fly apart. Instead, gravity keeps them in curved, closed orbits around a shared balance point called the center of mass. So, by watching these orbits, astronomers can unlock the key information, the masses of stars. So, let's look more closely at how that works. Now, the secret is something called the center of mass. You can see it illustrated here in the figure. First, imagine a seesaw with one child bigger than the other. We have a seesaw and there are two children. So, the heavier child has to sit closer to the middle so that the seesaw balance than the smaller child. And that middle point is like the system's balance point. Now, for stars, that balance point is called the center of mass. So, in this figure, that balance point is shown between star A and B. This is the center of mass, the point both stars orbit around, not around each other directly. So, notice how star A is drawn closer to the center of mass while star B is farther away. That's because star A is more massive, and the more massive star always ends up closer in, and the lighter star swings out farther, making a larger orbit. So, the center of mass is like the invisible pivot point of the whole system. So, next let's see how this affects the way we measure their masses. So, no matter where the stars are in their orbit, if you draw a line connecting them, it always passes right through the center of mass. You can see that in this figure. The line from star A to B always runs through that balance point, center of mass point. Now, the figure also shows two distances, RA, the distance from the center of mass to star A, and RB, the distance to star B. Later, we will use those distances to compare the stars' masses. And here's the important part. If we know the size of their orbits and how long it takes them to complete one orbit, their orbital period, we can use that information to calculate the total mass of the system. So, smaller orbits and shorter periods mean stronger gravity, which means the stars must be more massive to hold each other in place. So, the orbits themselves are the evidence. And by tracking these motions, we can use equations to unlock the combined mass of both stars. So, now that we have seen how stars orbit around their common center of mass, the natural question is, how do we turn those orbital motions into actual numbers for their masses? And the answer comes from K plus third law in the form Newton generalized for any two bodies. Remember, we learned about the K plus third law in a previous chapter. MA plus MB equals to A to the power cube over P square. Here A is the average separation of the two stars measured in astronomical units, and P is the orbital period measured in years. And MA and MB are the masses of the stars measured in solar masses. Now this is the Kepler's third law in the form Newton generalized for any two bodies. Now Kepler originally discovered this law for planets orbiting the Sun, but Newton extended it. It works for any two bodies orbiting each other. And that's why it's so powerful for binary stars. So if we know their orbital period P and how far apart they are on average A, this law lets us calculate the combined mass of both stars together. Now here's the catch. The equation only works cleanly if we use the correct units. Separation in astronomical units, period in years, and then the answer comes out in solar masses. But if we mix units, say kilometers instead of AU or days instead of years, we would have to add messy conversion factors. And that's why astronomers always translate observations into these standard units first. So in short, Kepler's law gives us the recipe: orbital size and period in, total stellar mass out. Alright, now let's work through an example step by step so you can see exactly how the numbers play out. Now suppose we have a binary star system with an average separation of A equals 16 AU astronomical units and an orbital period of P equals to 32 years. Now the question is, what is the total mass MA plus MB of the system in solar masses? So let's use our equation. MA plus MB equals to A to the power 3 divided by P to the power 2. So that means A equals 16 and P equals 32. So just substitute the numerical values. And now by calculating we get MA plus MB equals to 4. So this binary system has a combined mass of 4 suns. Alright, now that we can find the total mass from the orbital size and period, the next step is to split that total mass into the two individual star masses. So we can do that using the inverse relationship between each star's mass and its distance from the system's center of mass. So the equation is MA over MB equals to RB over RA. Here RA and RB are the distances from the center of mass to star A and B. So in words, mass ratio is equal to the inverse of orbit radius ratio. So the more massive star sits closer to the center, so it has the smaller r. Now the diagram shows the center of mass between star A and star B and labels RA and RB. So that picture is exactly where the ratio above comes from. The heaviest star is nearer the center, so its r is smaller, and the lighter star's r is larger. Now the total mass is MA plus MB and the ratio is MA over MB. And by solving these two equations, you can find MA and MB. We will do an example next to see how to do that. Now remember, the distances RA and RB must be true physical radii in astronomical units, not just apparent angular separations. So convert angular orbit size to physical size using the system's distance. And if the orbit plane may be tilted relative to our line of sight, you might correct for inclination or tilt to get true radii. Alright, now let's apply what we learned about mass ratios to a real binary system. So we already calculated the total mass. MA plus MB equals to 4 solar mass in the previous example. Now suppose the distance from the center of mass RA is 12 AU for star A and RB is 4 AU for star B. So what are the individual masses? So let's compute the mass ratio using the inverse rule. MA over MB equals to RB over RA. See here, it's not RA over RB, it's RB over RA. So that's what we call inverse rule. Okay. Now let's plug in the values. RB equals 4 astronomical units and RA equals to 12 astronomical units. So this gives you MA equals to 1 over 3 times MB. That means the more massive star is closer to the center, so MA is smaller relative to MB using the inverse of their distances. Now let's use the total mass. Ma plus Mb is 4 solar mass. We just found it in the previous example, right? So let's substitute Ma equals to 1 over 3 Mb in this equation. So by substituting and solving, we get 4 over 3 times Mb equals to 4 solar mass. So from here we get Mb equals to 3 solar mass. And then we can solve for Ma. So Ma would be 1 solar mass. So the answer is Ma is 1 solar mass and Mb is 3 solar mass. So notice how this matches the figure we saw earlier. The more massive star, 3 times the solar mass, is closer to the center, and the lighter star, 1 time solar mass, orbits farther out. So this completes the full process from observing orbits to calculating individual stellar masses. Now before we move on, let's quickly talk about some of the real-world challenges astronomers face when measuring stellar masses. First, orbits are not always perfect circles. Many are elliptical. And also, the plane of the orbit can be tilted relative to our line of sight, which can distort what we observe. And to get accurate masses, astronomers must correct for these tilts and eccentricities. And the apparent angular size of an orbit also depends on knowing the distance to the system. So that conversion is critical. So this process shows how science works. We start with observations, apply physical laws, and carefully correct for distortions to finally determine the masses of stars. Alright, now with this we conclude the section 5 of our chapter. So in section 5 we learn how binary stars reveal the masses of stars, why mass is crucial for a star's life story, and the careful steps needed to get accurate results. Now with that understanding, we are ready to move to the next section, the census of the stars, where we look at the distribution of stars in our galaxy and beyond. Alright, let's start with the idea of a stellar census. Just like governments count people to understand a country's population, astronomers take a census of the stars to understand what kinds of stars exist in our galaxy. So this gives us a big picture view of the universe. What's common, what's rare, and where our sun fits in among billions of other stars. Now the main goal of the stellar census is to describe the average star in the universe. So astronomers do this by measuring several properties of stars. Luminosity, or how bright the star really is, temperature, which affects the star's color, and size, how large or small the star is, and mass, how much material it contains. And by combining all these measurements, we can build a kind of family portrait of stars, showing everything from small, cool red dwarfs to huge, hot blue giants. Now, why do we need to survey so many stars? Because stars are not all the same, and understanding their differences tells us about how they form and evolve. So, surveys help astronomers find relationships, for example, how a star's mass affects its temperature and lifetime. And modern surveys use automated telescopes that take millions of digital images each night. So computers then analyze the data and store it in massive star catalogs. And these catalogs let scientists study patterns across millions of stars instead of just a few dozen. And interestingly, we don't have to look across the whole galaxy to get meaningful data. The stars near our sun, within a few hundred light years, are a good example of the Milky Way as a whole. So by studying these nearby stars in detail, astronomers can infer what the rest of the galaxy looks like. So even though we only see a small part of space, it gives a realistic picture of what most stars in the universe are like. So to sum up, the stellar census tells us That stars come in many varieties, but our sun is quite typical, an ordinary star in a very ordinary neighborhood. Now that we know why astronomers take a census of the stars, let's look at how they actually do it. Now, to understand the overall makeup of the galaxy, astronomers start close to home by surveying the stars around Earth. So, when scientists perform a local stellar census, they usually focus on all the stars within about 62 parsecs, or roughly 200 light years from Earth. And that might sound like a small distance on a galactic scale, but this region contains tens of thousands of stars, enough to give a reliable sample of what kinds of stars exist in our galaxy. So, by studying this nearby region, astronomers can estimate how common different types of stars are, from large bright blue ones to small faint red ones. Now on the image here, you can see Earth in the center of a survey sphere that extends out 62 parsecs. And each labeled dot represents a well-known nearby star like Sirius, Procyon or Delta Canis Majoris. So this diagram helps visualize how astronomers map and classify the stars around us to create a detailed neighborhood map of our section of the Milky Way. And once all those stars are counted and categorized, the results are actually surprising. The bright, massive stars that dominate the night sky, like Sirius or Vega, are extremely rare. And they look prominent only because they shine so brightly that we can see them from great distances. Now, in contrast, the red dwarfs, small, cool, and dim stars, make up the vast majority of stars in our neighborhood. And there are so many of them, they are the most common type of star in the galaxy. But they are too faint to be seen with the naked eye. So the stars we see in the night sky are not typical of the stars that exist. Now that we have looked at the variety of stars in our stellar neighborhood, let's focus on how mass and luminosity relates to a star's life. One of the most powerful tools astronomers use for this is the HR diagram. So this diagram helps us visualize patterns that hint at how stars are born, age, and eventually die. Now when we plot luminosity against temperature for a large number of stars, distinct regions emerge. And most stars fall into three categories: main sequence stars, giants, and white dwarfs. And the main sequence is especially important because it shows a clear trend in mass. And along the main sequence, stars are arranged by mass. The upper left portion of the diagram contains the hot, luminous O-type stars, which are the most massive. Next, moving down and to the right, stars become cooler, dimmer, and less massive, ending with the small, faint M-type red dwarfs. So this systematic trend of mass is one of the most fundamental patterns astronomers use to study stellar evolution. But stars that have evolved off the main sequence, such as giants and supergiants, do not follow this neat order, and their masses are more scattered. Some supergiants are very massive, while other giants are less so. So in general, these stars represent later stage of evolution, and their brightness or size no longer directly indicates their mass. Now let's look at the HR diagram again. It's labeled with stellar masses. The horizontal axis shows temperature decreasing from left to right, while the vertical axis shows luminosity increasing upward. And spectral types are labeling along the top from O to M. Next, the main sequence stars run diagonally from the upper left to the lower right. Notice the Sun in the middle as a G-type star with one solar mass. And giants and supergiants are scattered above the main sequence, and white dwarfs are found below. So pay attention to the mass labels along the main sequence. The trend is clear. Mass decreases from the top left to the bottom right. Giants and supergiants, however, do not follow a specific order. Also remember that the relative sizes of the stars on the diagram are not to scale. So in summary, the main sequence show a clear relationship between mass, luminosity and temperature, decreasing systematically from massive O-type stars to low mass M-type red dwarfs. And giants and supergiants have more scattered masses because they are in later evolutionary stages. Alright, now let's see how this mass affects a star's brightness or luminosity through what is called the stellar mass luminosity relation. And this is one of the most important relationships in astronomy because it shows how a star's mass controls how much energy it emits. Now for main sequence stars, the luminosity of a star compared to the Sun can be estimated using a simple equation. L over L Sun equals to M over M Sun raised to the power 3.5. So this equation tells us that even a small increase in mass results in a very large increase in luminosity. So for main sequence stars, luminosity rises sharply with mass. Now for example, a star with 4 times the mass of the Sun. That means star mass is 4 times the solar mass, right? So it has a luminosity roughly 4 to the 3.5 power or about 120 times the Sun's luminosity. So this demonstrates that a moderate difference in mass causes a huge difference in brightness. And it's important to note that this relation is an approximation. It works well for most main sequence stars, but stars that are not on the main sequence like giants, supergiants, white dwarfs or brown dwarfs do not follow this rule. So this law is specific to the main sequence. Now let's look at this graph. The graph plots luminosity versus mass for stars. And the red line represents the L proportional to M to the 3.5 power relation. So you can see that the open circles representing white dwarfs do not follow the line because they are not main sequence stars. Notice the huge range of luminosities covered in this figure. The graph includes stars from about 0.1 solar masses to about 100 solar masses, a factor of 1000. But their luminosities ranges from a few 10,000s of the Sun's luminosity to over a million times the Sun's luminosity. And this shows just how sensitive luminosity is to mass. Now to summarize, the stellar mass luminosity relation shows that small difference in mass led to dramatic differences in luminosity for main sequence stars. So this relationship is fundamental in stellar astronomy and helps astronomers understand how stars generate energy and evolve. Remember, non-main sequence stars do not follow this simple relation. But for main sequence stars, it provides a powerful tool for predicting luminosity from mass. Alright, now that we understand the mass-luminosity relation, let's see it in action with a practical example. So let's calculate the luminosity of a star that has 4 times the mass of the Sun. So this will help us see just how dramatically luminosity increases with mass. We just did the calculation in the previous slide, right? But let's try again. So let's start with the mass-luminosity relation for main sequence stars. Here, L over L Sun is the star's luminosity relative to the Sun, and M over M Sun is the star's mass relative to the Sun. Now the problem tells us that the star has a mass of 4 solar masses. So by substituting into this equation, we get L over L Sun equals to 4 to the power 3.5. So the luminosity of a star with 4 times the Sun's mass is 128. And this means a 4 solar mass is about 128 times more luminous than the Sun. So notice how a relatively moderate increase in mass produces a huge increase in luminosity. So this illustrates the steep nature of the mass-luminosity relation. Now so far we have explored mass, luminosity and how they relate on the main sequence. Now let's turn to another fundamental property of stars, density. And understanding density gives us insight into how stars are structured internally and how different types of stars compare. Now, density is defined as mass divided by volume. So, in mathematical terms, average density equals mass over volume. But stars are not uniform in density and their cores are much denser than their outer layers. For example, the center of the sun is about 150 times as dense as water, while near its visible surface, the density is less than 1/3000th the density of Earth's atmosphere at sea level. So the average density gives a useful overall measure, but the interior can be dramatically different. And with stars vary enormously in density depending on their type. For example, main sequence stars like our sun have densities roughly 1.4 grams per cubic centimeter, which is just slightly denser than water. And giants and supergiants are extremely diffuse, with densities ranging from about 10 to the minus 7 to 10 to the minus 3 grams per cubic centimeter. And that is far less dense than air on Earth. So these stars are enormous in size. So even though their mass may be high, their volume is huge, resulting in low density. Next, white dwarfs in contrast are incredibly dense. They have masses similar to the sun but are compressed into a volume roughly the size of the Earth. So this makes their densities millions of times greater than water. So dense that a teaspoon of white dwarf material would weigh several tons on Earth. So density is not just a number. It helps us categorize stars into three evolutionary groups: main sequence stars, medium density; giants and supergiants, low density; and white dwarfs, high density. So this categorization reflects the life stages of stars. Main sequence stars are stable and burning hydrogen in their cores. Giants and supergiants have expanded during late evolutionary stages, and white dwarfs are the dense remnants left after a star has exhausted its fuel. Pretty amazing, right? So, in summary, density varies dramatically across different types of stars, providing a window into their internal structure and evolutionary state. So, main sequence stars are moderately dense, giants and supergiants are very diffuse, and white dwarfs are extremely compact. So, understanding these density differences is crucial as we continue to study how stars live, evolve, and eventually die. Alright, class, now with this, we conclude chapter 9 on mass, luminosity, and density of stars. Next, let's go over the chapter summary to review the key points we have learned so far. Now, first we discussed star distances. Remember, measuring the distance to a star is fundamental because we can only determine other properties of a star once we know how far away it is. And astronomers measure distances using stellar parallax, which is the apparent shift in a star's position when observed from different locations. Next, distances are usually given in parasecs, where 1 parasec is equal to about 3.26 light years. And we also talk about the proper motion, which is how fast a star moves across the sky. Nearby stars tend to move faster. So next we discuss about brightness and luminosity. A star's apparent brightness is how much light we see from Earth, and it decreases with distance according to the inverse square law. And to compare stars fairly, we use absolute magnitude, which is the brightness a star would have if it were at a standard distance of 10 parasecs. And finally, luminosity is the total energy a star emits per second, including all wavelengths, not just the visible light. So this gives us a full picture of the star's energy output. Alright, next let's review stellar spectra. Now the absorption lines in a star's spectrum tells us a lot about its temperature. In cold stars, the hydrogen bomb lines are weak because the atoms are not excited. But in very hot stars, the lines are also weak because the atoms are ionized. And the lines are strongest at intermediate temperatures, around 10,000 Kelvin. So using these lines, astronomers classify stars into spectral types O, B, A, F, G, K, M, from hottest to coolest. Remember? And we also talked about brown dwarfs, which are cooler than M stars and have their own spectral types. And next, section 4 is all about star sizes and their chart diagram. So we can estimate a star size by comparing its luminosity to the sun. And the chart diagram plots luminosity against surface temperature and helps us categorize stars. And most stars, including the sun, are on the main sequence. Giants and supergiants are much larger and have low density atmospheres, while white dwarfs are small and extremely dense. And spectral line widths also help classify stars into luminosity classes. 5 for main sequence, 3 for giants and 1 for supergiants. Right? Next we focus on star masses and the census of stars. The only direct way to measure stars' mass is by studying binary stars, where two stars orbit a common center of mass. And we discussed how to measure the stars' masses and sometimes their diameters based on their orbits and light curves. And in the last section, we looked at the census of stars and the mass luminosity relationship. So in our neighborhood, most stars are lower main sequence stars. White dwarfs are fairly common, while giants and supergiants are rare. And for main sequence stars, more massive stars are also more luminous. Next, we also reviewed star densities. Main sequence stars have similar density to the sun. Giants and supergiants are very low density, and white dwarfs are extremely dense. So this gives us a complete picture of how stars differ in size, mass and structure. So that's the end of chapter 9, the family of stars. So I encourage you to go through the review questions and problems to deepen your understanding about this chapter.